discrete time Markov chain, I am going to give the formal definition of a discrete time Markov chain. Formal definition of discrete time Markov chain. In notation, we call, in short, we call it as a DTMC. Consider a discrete time, discrete state stochastic process. Consider a discrete time this is a discrete time, discrete state stochastic process. Assume that xn takes a finite or countable number of possible values. Unless otherwise mentioned, this set of possible values will be denoted by the set of non-negative integers s is equal to 0, 1, 2 and so on. Unless otherwise mentioned, you can always assume that the state space S consists of the element 0, 1, 2 and so on. Even if it takes other values also, you can always make a one-to-one correspondence and make the state space is going to be S is equal to 0, 1, 2 and so on. Suppose the probability of the xn plus 1 will be taking the value j, given that it was taking the value x naught is equal to I naught, x1 was I1 and so on, and xn was I. That probability is same as the probability of xn plus 1 will be j, given that xn was I for all states, I naught, whatever be the value of I naught, I1, I and j, and also for all n greater than or equal to 0. If this property is satisfied by for all states I naught, I1, I comma j, as well as for all n greater than or equal to 0, then this stochastic process, that is a discrete time, discrete state stochastic process, is going to be known as a discrete time Markov chain. So, basically this is the Markov property, and the Markov property is satisfied by all the states as well as all the random variables. So, if this Markov property is satisfied by any stochastic process, then it is called a Markov process, and since it is the time space is discrete and the parameter space is discrete, therefore, it is called a discrete time Markov chain. Then we say this stochastic process xn takes value n starting with 0, 1, 2 and so on, is the discrete time Markov chain. We can just have a look of how the sample path look like for different value of n, and the y axis is xn. Suppose at n is equal to 0, it started with some value. At x is equal to n is equal to 1, it would have been the different value, and n is equal to 2, it would have been the different value. So, these values are the either it could be a finite value or countably infinite number of values. Therefore, the state space is going to be discrete and the parameter space is going to be discrete. So, like that it is taking a different value over the n. So, this is going to be the sample path or trace of the stochastic process xn. Suppose you assume that xn is the state of the system at nth step, or nth time point, and this xn satisfies the previous this Markov property, then the stochastic process is going to be called it as a discrete time Markov chain. And our interest will be, suppose the stochastic process satisfies the Markov property, our interest will be to know the two things. One is, what is the distribution of xn for n is greater than or equal to 1. You know where the system starts. So, x naught you know, your interest will be what could be the distribution of xn, that is nothing but what is the probability that the xn will be in some state j, and also what could be the distribution of xn as n tends to infinity. As n tends to infinity, or our interest will be finding out the distribution of xn. So, at any finite n as well as n tends to infinity, that will be of our interest. To compute this, you need two things. One is, you need what is the distribution of x naught, that is the initial distribution vector, where the system starts at the 0th step. What is the distribution of x 0? And also second things of your interest will be, what is the transition distribution, or how the transition takes place. What is the distribution of a transition from any nth step to n plus 1th step for all n. So, if you know the two things, the initial distribution vector as well as the distribution of the transition from nth step to n plus 1th step, using these two quantity you can find out what is the distribution of xn for any n, as well as you can find out the distribution of xn as n tends to infinity. For that, I am going to define few conditional probability distribution as well as the marginal distribution for the random variable xn. Through that, we are going to find out the distribution of xn for any n as well as n tends to infinity. So, the first one I am going to define the probability mass function as the p suffix j of n, that is nothing but what is the probability that xn takes the value j. So, this is the probability mass function of the random variable xn. What is the probability that xn takes the value j? That I am going to denote it as the p suffix j of n, where here the j is belonging to the state space capital S. This is the probability mass function of the random variable xn. Similarly, I am going to define the conditional probability mass function as a p suffix j k of n, that is nothing but what is the probability that xn takes a value k given that I need two suffixes, two index for here with the two variables m comma n. What is the probability that xn will be the state k given that xm was j. Obviously, the m is lies between 0 to n, whatever m and every n, and the j comma k is belonging to capital S. So, this is a conditional probability distribution of the random variable xn with the xm, and at the mth step the system was in the state j, and the nth step the system is in the state k, and this is a conditional probability with the two arguments m comma n. So, this is a probability that the system makes a transition from the state j at step m to the state k at step n, and this is called a transition probability function of the discrete time Markov chain. When the DTMC is a time homogeneous, this is very important, when DTMC is a time homogeneous, that means it satisfies the time invariant property. That means the p j k of m comma n depends only on the time difference n minus m. Whenever the DTMC is a time homogeneous, that means in the time invariant. So, the actual time is not a matter, only the time difference is the importance. Therefore, this is going to depends only on the time difference n minus m. In this case, I do not want the two arguments m comma n, I can go for writing p j k of n, that is nothing but what is the probability that in the m plus nth step the system will be in the state k, given that in the mth step it is in the state, it was in the state j for all n and here j comma k belonging to S. So, the m does not matter, only the interval or the interval length of step n is matter. So, that means the system was in the state j and it is a transition into the state k in n steps, because the DTMC is a time homogeneous. So, the x m to x m plus n, it is valid for all m. For all n, we are finding out for the n step transition. This is called a n step, because the DTMC is a time homogeneous, and this is called a n step transition probability function. This is the n step transition probability function. Using this, we can define the one step transition probability, that is denoted by p suffix j k of 1, or we can avoid the bracket 1 also. So, you can write it as the p j or p j k, that is nothing but what is the probability that the x n plus 1 is equal to k, given that x n is equal to j for all n greater than or equal to 1. Obviously, for j comma k belonging to S, if you find out the 0 step transition probability, that values is going to be 1 for j equal to k, otherwise it is going to be 0. This one step transition probability, I can make it in the matrix form, as the capital P is the matrix, and that consists of P I j, where the P I j is nothing but one step transition probability mat elements of x n plus 1 is equal to j, given that x n is equal to I. Here I comma j belonging to the state space S. You should remember that the state space S is consists of finite elements or countably infinite number of elements. Accordingly, this matrix is going to be either when S is going to be a finite elements, then the P matrix is going to be a square matrix. Since the Pij is the one step transition probability of a system moving from the state I to j in one step, and since it is a time homogeneous, this is valid for all n. This is valid for all n greater than or equal to 1, and this satisfies the one step transition probability matrix satisfies two properties. The each entity will be greater than or equal to 0 for all I comma j belonging to S, because these are all only the conditional probability of system moving from the state I to j in one step. Therefore, either it will be a 0 or greater than 0 for all possible values of I comma j. The second condition, if you make the summation over j for fixed I, then that is going to be 1, I belonging to S. That means the row sum is going to be 1, because it is a conditional probability of system moving from one state to all other states. If you add all the other possible probabilities, then that is going to be 1. And since this one step transition probability matrix satisfies these two properties, and this matrix is P is known as a stochastic matrix. Because of satisfying these two conditions, the matrix one step transition matrix is also called a stochastic matrix. Now, I am going to explain what is the pictorial way of viewing the one step transition probability matrix or the stochastic matrix. That is provided by state transition diagram, or the other word, it is called a directed graph. The DTMC can be viewed as a directed graph such that the state space S is the set of vertices or nodes, and the transition probabilities, that is a one step transition probabilities, or the weights of the directed arcs between these vertices or nodes. Since the weights are positive and the sum of the arc weights from each node is unity, this directed graph is also called a stochastic graph.